Hello everyone, and welcome to week 6 of Math 520. This week, as you know, we're having our midterm tests. We have our orals the first part of this week, and then afterwards we're going to have the written part. So because of that, this week we're going to go a little bit light on the content, and we're going to talk a little bit about determinants and a little bit about geometry. So we will see some examples of some try to visualize what a linear transformation is doing and try to make sense of the idea of a determinant of a matrix. So that's going to be the material for this week. That's going to be taken out of Trail's book, Linear Algebra Done Wrong, and also just sort of taking it from my slightly idiosyncratic point of view on the determinant. Also, because this week is the the midterm week, we're going to skip out on the homework and discussion that's normally due. So none of that will be due this week, though of course you're welcome to post to Piazza as you would like. Here's a visualization tool for understanding what the geometry is of a linear transformation. So here, for instance, let me start with the identity matrix. And let's take a look at what right here, let me put a few other things, right? So we have, on the left here, we have the domain, and on the right, we have the codomain. And this is the identity map, right? It sends every vector just to itself again. So here, on the domain, I have the unit circle. I have this vector here that I can move around, and on the right we have the image. Okay, so now what I'm going to do is I'm going to change my matrix so that it is 2, 0, 0, 1. So then having a 2 in this upper position causes, right, this is stretching it out by a factor of 2 in the x direction, but in the y direction it stays the same. Right, so if I start with a vector that's a vertical vector, nothing happens to it. It gets mapped to itself. But then if I start increasing the horizontal component, it gets stretched out in the x direction. And the extreme form of that is if I go down to the x-axis, my vector gets doubled. So that's an example of a linear transformation. And in general, right, if I go and I stick some other constants on the diagonal, so here I have, for instance, I have a 2 here, right? That's just scaling everything by a factor of 2. If I put, let me put some 1s on the diagonal here and put maybe 1 on the off diagonal, then that one's a shearing transformation, right? So that's what that's doing is you see how it transforms the grid, and actually here's a little n that they kindly provided us. It is this sort of zigzag n. The output of that, it gets sheared over. And if I can make the shear factor be very large, and it just sort of squishes everything over to the side. And I can, right, so in general, if we have a more complicated matrix, let's say I get a 1 there and maybe a -1 there, then the result of that looks an awful lot like a rotation together with the scaling. And so that's an example of something that looks like a composition of rotation with the scaling. If I go and I maybe muck around with it a little bit, this one looks like there's a bit of a rotation, a bit of a scaling, and a bit of a shearing operation going on. So in general, we want to understand these linear transformations as some combination of more basic geometric operations. Right? So we can think about scaling, we can think about rotation, we can think about shearing as basic geometric operations. Right? So that's sort of the goal of what we're going to think about. We're going to try to understand if we can decompose a linear transformation into these basic constituent pieces of what it's actually doing. So that's one of the important goals in understanding the geometry of linear transformations. And as you may remember from Cal 4, there's a very useful description having to do with area. So if I think about this matrix acting on the plane, right, I can ask myself, let's go back to the identity matrix here. So here I have the identity matrix again. Oops. Right, so this is my identity matrix. One of the things we're going to be interested in is what does it do to this unit square? And I have this unit square here in the domain. That unit square is what we get by looking at the standard basis. Right? So the basis defines a little square for us, this first little square in my grid. And we want to look at what happens to it in the output. Right, so if I scale in one direction, right, so here I'm scaling by a factor of 2, then that little square there becomes a little rectangle. Right, it's a 2 by 1 rectangle, so the area of that becomes 2. If I scale in both directions by a factor of 2, then my little square becomes a bigger square. Right, this 1 by 1 square gets mapped to a 2 by 2 square. And so we find ourselves with something of area 4. So this is what we're going to want to think about in terms of the behavior of our matrix, right? We're going to want to understand our matrix in terms of how does it transform the area of this little square in the domain to some parallelogram in the output. So that's going to be the first question we're going to look at, and then we're going to see how that generalizes in higher dimensions. These ideas are developed more carefully in Trail Chapter 6, specifically sections 6.1 and 6.2. But let me say a few words about it and where it's coming from to sort of maybe draw some pictures that will help illustrate the ideas. Okay, let's take a look at area and really try to understand some of the key properties of area in the plane. So the 3 properties of area we're going to focus on are going to be the ones that generalize for the determinant in understanding it as something in higher dimensions. So what we're going to do is we're going to think of area as being a function that depends on 2 vectors. Right, so let's think about area in the plane. We're going to think of it as a function of 2 vectors. And what it is it's going to be the signed area of the parallelogram that we get by looking at, let's say, the vector v1 and a vector v2. And so we're going to get the signed area of that thing. We're going to say that it's positive. It's going to be positive if these are in a counterclockwise order. And so v1, v2 are in a counterclockwise order. And we'll say it's less than 0 if v1 and v2 happen clockwise. Okay, so the first obvious thing we get out of that is that area of v1, v2 is going to be minus the area of v2, comma v1. Okay, so that's a property that comes to us just from the signed convention. And then the next thing we have is also an obvious thing, is if I take E1, E2, right, the standard basis for R2, then the square that I get from them has area 1. So we're gonna take that as a definition. So that's going to be a defining like a defining feature of the area, right? It's a normalization. It's telling us what units we're using for the area. Okay, and then the last property we have actually has 2 sub-properties that I'm going to describe in a second. So what we're going to show is let's justify the third property, which is that the area of v1 and v2 is linear in each argument. That means that the area of, let's say, alpha v1 plus beta v1 prime comma v2 is the same thing as alpha times the area of v1 comma v2 plus beta times area of v1 prime comma v2. And then the same deal if I did the thing in the v2 coordinate. So why is this true? Okay, so let's break this down into two pieces. Right, the first one is, why is it true for the scaling? And for this, we're going to think about this in with alpha positive and alpha negative. And if I think about it for alpha positive, we're going to have, and so here's a vector v1, here's a vector v2, and we're scaling v1 by some factor alpha. Well, let's think about what the area is. Right? The area of this parallelogram here, I can get it by taking the base here, and I multiply it by the height. Right? So that's the height h, and then that's base. So base times height is the area of my parallelogram. Well, my big parallelogram here, right, my big parallelogram, has a different base but the same height. And all that happens to the base is we've multiplied it by alpha. So that much just follows from geometry. Right? So that's, that formula checks out when alpha is positive. And then when alpha equals -1, we get, right, so here's v2 again, here's v1, let's say. Well, minus v1 is the same thing flipped over. So these two rectangles are going to be congruent, right? Those two, sorry, not rectangles, those two parallelograms are congruent. So they have the same area if you forget about the sign. And then here you notice that if v1 comma v2, if that pair happens in the counterclockwise direction, then negative v1 comma v2 happens in the clockwise direction. Right? So this shows that area of negative v1 comma v2 equals minus the area of v1 comma v2. So putting these two observations together, we get this first bullet point here, that the area scales correctly. Right? And the same argument applies whether it was v1 or v2, right? So I'm not going to repeat the argument for scaling in the second factor. Okay, so then the other half of this property is that the area of, let's say, v1 plus v1 prime comma v2, that should be equal to the area of v1 comma v2 plus the area of v1 prime comma v2. Well, let's draw a picture. So there's a picture here for the left-hand side. Right? Let's say I have here, let's say that's v2, and here is, let's say that's v1. Then we get this parallelogram right here. And then instead of drawing, let's draw that guy as again the vector v2, and let's draw here, let's say that's v1 prime. And so here I get, oh, my parallelogram is not very good, but let's say we get this parallelogram. Okay, and then let's draw over here, let's draw the sum v1 plus v2. Well, the sum v1 plus v2 is this guy. Right, so that's going to give me here v1 sorry, not v1 plus v1 prime. And v2 up here is that guy. So here we get this parallelogram. Okay, I didn't make that convincingly long, but that parallelogram, we see it in this picture over here as that. Right? So that green guy is the one on the left. The two that I'm going to circle in this dark blue are the ones on the right. Right, so that's this guy plus that guy. And then here I'm going to color in, right, that's a difference between the two, and that's a difference between the two. And if you check, right, those two triangles that I colored in red are congruent. Right, so the two blue parallelograms pick up this bottom red triangle too much, and they're missing that top red triangle to match the green one. Right, so these two red triangles compensate each other, and we're left then with equal area. So that checks this one out, and then our linearity property follows from that. So this is what we're going to do. We're going to use this property and make it a definition. We will say that the determinant of a collection of vectors, let's say v1 up to vn, where v1 up to vn are in Rn, we're going to define it by its properties. We're going to say the first property is that the determinant of E1 up to En is equal to 1. The next property is that the determinant of v1 up to vn flips a sign if we swap two vectors. Right? So let's say there's a vj here in the middle. Let's put vj here, a v1, and then vn. Right? So we get that if we swap two vectors, the sign changes. Now, it doesn't matter which two vectors you swap. If you swap any two vectors, you get a sign change. And then finally, the final property is that we want the determinant of v1, v2, etc. up to vn. We want it to be linear in each of the n arguments. Right, so if we think of it as a function of n variables, right, it takes n vectors as an input. I want us to think of it as being linear in each of the n variables. Okay, and there's a name for each of these properties. Well, I guess this one. Right, this is, we say it's antisymmetric or alternating. And this last one is called multilinearity. And a piece of fantastic, almost magic, is that these three properties are enough to describe the determinant uniquely. So the two things that are maybe, right, there are two pieces to that. One is that it exists. And the second is there is a unique function that has all of these properties. And that thing is the determinant. And then there are many different formulas possible for the determinant, many different descriptions of it. But this is the basic, surprising, and deep fact about the determinant.